Series, sums of squares and cubes. In the previous section, we looked at showing that the sum of all of the ones, we found that was a linear sequence, and that the sum of the first natural numbers gives a quadratic. This can then be expanded, so if we want to find the sum of the squares, gives us a cubic, and to get a quartic, well, that's the sum of the cubes. Here we can see some formulae written out in more detail underneath. We will come back to these to prove them when we do mathematical induction. Example 5, and I've left the two formulae just above so we can refer to them. We want to first of all, in part A, to evaluate the sum of the series r squared from the 20th term to the 40th term. So hopefully you can remember that that is the same as going from the first term to the 40th, and from that subtracting the first to the 19th of the r squared. Now we can use a formula for this. So we're going to use the formula a 6n, n plus 1, 2n plus 1. So this first one, filling those in, we have a sixth, n is 40, 40 plus 1 is 41, 40 times 2 plus 1, 81, and from that we're going to subtract, in time n is 19, 19 plus 1 is 20, 2 times 19 plus 1 gives us 39. Taking our calculator and working that out gives us 19,670. Now for part B. In part B, we want to find the sum of the cubic terms from the 1st to the 25th. Now we're going to use the formula which you can see up here, a quarter n squared times n plus 1 in brackets squared. So we have a quarter, this time n is 25, squaring that. Then we have 25 plus 1, squaring that. Taking our calculator gives us an answer of 105,625. Example 6. Here we have the sum of the r squared, going from r equals n plus 1 to 2n. So the first thing I'm going to do is bring down the formula for the r squared. So we can refer to it. Well, to go from n plus 1 to 2n for r squared, we need to first of all sum from the first term to 2n of r squared, and from that we're going to subtract from the first term to the nth term of r squared. Now, using our formula gives us a sixth. N in this case is 2n, as you can see. 2n plus 1, and then be careful here because it is 2 times 2n plus 1, and from that we're going to subtract a sixth. This time n is n, so n plus 1, 2n plus 1. Now we can tidy that up a little bit. It is critical at this time just to take our time with these, because quite often you will find there are lots of common factors. So, looking through this, what is common? First of all, a sixth is common. N is common, as is 2n plus 1. So, what do we need to fill in here? Well, we have, looking along our first one, we have a 2 and we have a 4n plus 1. And looking along the second one, Well, we have our sixth, our n, and our 2n plus 1, so we need to put in our n plus 1. So minus n plus 1. Tidying that up gives us 2 times 4n is 8n, plus 2, minus n minus 1. Being careful here because this is where most mistakes are made. Eight n take away n is 7n. 2 minus 1 is 1. And we have our result. Now to look at part B, which says verify that the result is true for n equals 1 and n equals 2. Well, for n equals 1 first of all, that means 1 plus 1 is 2, 2 times 1 is 2. So as you can see, we have from 2 and 2 the sum of r squared, which gives us an answer of 2 squared, which is 4. Now to verify, we have to check our formula. We can see that that is a sixth n, 2n plus 1, 7n plus 1. So subbing in 1 for each of the n's gives us the following. Here you can see a sixth times 1, 1 filled in for each of the n values. Calculating that gives us a total of 4. So therefore, that is verified. For the second one, for n equals 2, filling in n equals 2. Here we can see, well, 2 plus 1 is 3. 2 times 2 is 4. Checking that, here we can clearly see it would be 3 squared plus 4 squared, giving a total of 2. And then checking our formula gives us the following. And calculating that gives us 25. They're both 25. Sorry for that, erasing too much. So we've now verified both. And the question is complete. Example 7. In this example, we want to show that the following summation can be rewritten as the following formula. So let's look at part A. Well, our summation from 1 to n of r squared plus r minus 2 can be rewritten as the sum of r squared plus the sum of r minus 2 times the sum of all the 1's. Now, using our formula for this gives us sum of r squared is a sixth n, n plus 1, 2n plus 1. The sum of the r terms is a half n, n plus 1. And finally, the sum of all the 1's n times is n, so times 2 gives us our 2n. Next, we need to try and simplify this. Well, to simplify this, one way of factorising, the sixth n, we can think of that as being common, leaving us n plus 1, 2n plus 1, plus n plus 1, minus 12. Sorry, I've left out a bit there. There should be a 3 in there. So again, just worth double checking all of that. Sixth n times this first term gives me the first one. Sixth n times this, 3 over 6 is a half. And a sixth n times the 12 does indeed give me my 2n. Okay, next step. I have my sixth n outside first of all. Next, there needs to be some expanding out here. So 2n squared plus 3n plus 1 plus 3n plus 3 minus 12. Tidying this up, 2n squared plus 6n minus 8. And tidying this up further still, we have, we can see that they're all even numbers inside. So a sixth can become a third. And finally, this will factorise, giving us inside n plus 4, n minus 1, which is what we were looking for. Next, for part B, it says hence. So hence means we're going to use our result from part A to find the sum of the series 4 plus 10 plus 18 plus 28 plus 40, etc. up to 418. So, for part B, if we're going to use our formula, we need to know how many terms are in this sequence, this series. So thinking about this, well, what happens when r is 1? Well, our formula, remember, was r squared plus r minus 2. Well, if r is equal to 1, then r squared plus r minus 2 is equal to 1 plus 1 minus 2 is 0. Let's just check it with 2. 2 squared plus 2 minus 2 is 4. So we start to see that this looks like our series. Let's just check one more. R equals 3. 3 squared plus 3 minus 2 is equal to 10. So it does indeed look like that. Now, with a bit of trial and error, we can find that when r is equal to 20, 20 squared, 400, plus another 20, take away 2 gives us 418. So here we can see we actually want to find the sum of the first 20 terms of r squared plus r minus 2. And we know a formula for that, because we found this from part A. So now we can think, well, n equals 20, so this is equal to a third times 20, 20 plus 4, 20 minus 1, which gives us a total of 3040. And that concludes the question.